Yeah, thank you very much for the invitation. Thanks for the introduction. Indeed, I delayed the announcement of my title because I said there's two projects in the pipeline. Either would fit the theme. You would be the judge whether I was correct there. And I didn't know which one it would be. And it is going to be the big reveal party now. All right, it's going to be on Euler and not on Cayley. Oh well, okay. All right. So by the way, Euler, this is I've asked an artificial intelligence to draw a picture of Euler winking, and it did it. But it's also, I'm not sure how well you can see it because it's quite dark, no? But it's also quite dark themed, the picture, because as you might know, Euler had a near fatal disease at some point in his life, which left his right eye, left him blind on the right eye. So he couldn't move it anymore. And this bloody AI seems to have picked it up because he's blinking, but he's not quite closing his right eye. No. So then I thought that was too dark to display here in a presentation, but then I liked his wry smile, so anyway, put it here. Okay, so on Euler. Good. Here's the outline of my talk. It has two parts. The first is, okay, so the idea of this session here today, I guess, is to connect different communities. So I will talk a little bit about how I see the relation between time frequency analysis and quantum computing. And that has, again, two parts. One is a mathematical framework, which is basically just to synchronize language. I will tell you some definitions, and you will all nod along and say, I know, but just so that we are on the same page. And then I make some high-level comments, a bit maybe about philosophical differences, because somehow we are looking at the same subject matter, but there are surprisingly few collaborations, and I have a theory as to why that is, so I will. Yeah, and then I will actually talk on Euler. There's some quantum combinatorics, some star algebras, and some phase-space functions with low autocorrelations. So there's something in the bag for everybody. Good, so part one is time frequency analysis and quantum computing. And part one is a mathematical framework. So this is going to be very old slides I've recycled. I hope, I haven't looked at them in years. I hope I will remember what's on them. And yeah, it's just so we sync up on notation. Oh, by the way, I couldn't come earlier due to teaching obligations, but Hans, I watched your talk on YouTube in the train. The future has arrived, and I will refer to it occasionally. Right, to highlight differences and similarities. Okay, so time frequency analysis. What is the arena? So we start with a vector space of functions. Okay, yeah, I put L2 here because it was for a less discerning audience. Of course, you guys. I mean, for you the particular P here is very, carries a lot of meaning, but okay, so I didn't think about it too hard. So basically, we're talking about a vector space of functions that live on some configuration space, Rn, and are complex valued. And if we talk about time frequency analysis, then we have to have these two symmetries present, time shifts and frequency shifts. And so these are implemented by operators that go by under different names in different communities. We call them while operators. So there's the displacements for you in time, for us in space, but it comes down to the same thing, where you just take the function and displace it. And then there's a Fourier transformed version where you multiply the function pointwise by a character, which of course corresponds to boost in the Fourier domain, which you guys call frequency and we call momentum, but of course, again, it's the same thing. Right, so together they generate a group, they almost close up to some phase factors, which are of course very important. And these phase factors work out. So if you multiply these two operations together, you get, it's basically abelian. So the parameters just add up, except for you got this twist here, which involves a symplectic form on R2n. Okay, so that's how symplectic geometry enters the picture. And all right. So now we talk about symmetries. We can go one level higher, and we can now look at symmetries of this Heisenberg group itself. And we can look at the unitaries, which map these while Heisenberg operators onto themselves by conjugation. And then this turns out to be given by any such symmetry is specified in terms of a symplectic matrix and vice versa. For every symplectic matrix, you can find one of these symmetries. Right, and the appearance of the symplectic group is not surprising because the structure constant of the group encode, of course, a symplectic symmetry. And this has been discovered and rediscovered many, many times in different communities and has an annoying number of names, and nobody can agree on the details. So some call it the metaplectic representation of the symplectic group, the oscillator representation, bosonic Bogoliubov transformations, canonic transformation. I don't know. Like Clifford group, we call it in quantum information theory. So it's a very important structure, which you can tell by the fact that it gets rediscovered every few years. Okay, there's one more bullet point before I go discrete. So then, of course, very important set of vectors in this context are the complex Gaussians, right? So these are functions which are exponential. You got the negative quadratic form here, which gives you a Gaussian hull, and then some oscillatory part, some linear part here with an I in front. They're a rich family of functions that can be described efficiently using linear algebra. So these are high-dimensional functions, but you just give these matrices in this vector, and you can talk about their properties in terms of these or related matrices. And they form also an orbit under time frequency shifts and symplectic operations. So they are well matched to the symmetry of the problem. You all knew this, okay? Now let's go discrete, or it's unfortunately the word discrete has stuck here, but it's really finite. Yeah, it's not, discrete is wrong, but it's too late to change now. So now we take a look at the finite version. And again, the definitions are kind of close to what you heard about on Monday, but the philosophy is a bit different. I'll talk about this in a second. Okay, so first I change my vector space by changing the configuration space from a continuous vector space to a finite vector space, or if D doesn't need to be prime, then it's not even a vector space, but some module if you want. Yeah? So we have now a finite domain, and the functions here can now also be understood as tensors, right? Where I choose coordinates here and then specify the function just by its values on all of these coordinates. Okay, and everything I did, I can just repeat formally, and there's minimal changes, and the few changes I've indicated in red. So there is an additive, it's not, the index set is not just a set, it has an additive structure. So you can talk about shifts, all right? So the shifts work the same way, and this is the cyclic addition in that set. And there is, of course, also the dual group of characters, which now is parameterized by complex exponentials that take values in these words of unity. So the first modification is that I, restrict the characters a little bit by putting a D's word of unity there. And then again, we have a Heisenberg group, and it's now a Heisenberg group over a finite base space. And again, the commutation, like the group law is the same. And again, there is a symplectic form popping up. Naturally, I don't put it in, it's just there. And it's now a symplectic form on this discrete vector space. All right. And again, I can look at the symmetries of those. I can ask, what are the unitaries? These are now finite unitary matrices that map these phase-space time frequency shifts to themselves under conjugation. And again, you'll find these are a representation of the symplectic group. Just now, it's a symplectic matrices with integer values. And right, and yeah, in quantum in particular, we call this the Clifford group, the group generated by the symplectics and the time frequency shifts. We call the Clifford group, which is also very annoying because there's many different groups that go with the name of Clifford, and yeah, that always leads to confusion. Okay, there's 3 of 3. I'm almost done. There is another, and now comes the first difference maybe to what you heard on Monday. There is we can also talk about discrete complex Gaussians. But when I say that, they are different from the one I saw on your slide, because it looks very similar, but now all my coefficients here are also integer valued. And everything is imaginary, so there is no, hull anymore, right? So these are all roots of unity 2, the values that they take here. And so the picture that when you draw what you called discrete Gaussians, they still look like Gaussians just on discretized lattice. But when I draw discretized Gaussians, they look more combinatorial and more geometric. Yeah, there is no attenuation here anymore. Please. Why is there an I? Yes, okay. And so there is many ways of answering this question, but one way of answering this question is that I would like to retain the property that these test functions I talk about form an orbit under the symmetry group. And so they do, and if you mimic the real valued Gaussians with like a damping factor, then they no longer do that. Yeah, so these are the right objects that are adapted to the symmetry at hand. That's why we do it. Yeah. These are in fact, yeah, exactly. So in quantum information, they're called stabilizer states, and the stabilizer in stabilizer refers to a stabilization, namely to a stabilization by a group action. And so, of course, it's just a different way of talking about it. All right, very good. So you've seen that all. And this I wanted to skip, blah, blah, blah. These are all. Okay, good. So now we are on the same page when it comes to definitions. Now let me think a little bit about, like, go on a higher, a bit of a bird's eye view. That's right, I copy-pasted from the YouTube video. You're now a YouTube star. Yeah, I got now teenage kids, and they are all into social media, and then, they all want to be influencers. And literally, that's my big one. Yes, he wants to be an influencer. And then I can sometimes say, I'm on YouTube and I got more hits than you. You're also on YouTube. You got more hits than my daughter. Okay, good. Fine. Right. So why, even though we talk about the same objects, why maybe is there so little collaboration between the fields, or much less than there could be? And in fact, I wanted to link back to the workshop, because I guess this workshop apparently started with a paper by Reinhardt in '84, and so the 1980s, Reinhardt worked on analysis. It's an analysis paper, nowhere. IP spaces are very important, and convergence and stuff like this. And then from the 2000s on, Reinhardt worked on quantum information, and so they are related, but they're not the same. One difference is that this has 25 times more citations. So you would think that quantum information is 25 times as valuable to society if you are a university administrator. Of course, we know it's just 25 times as much hot air, but okay. All right, so, and so there's good news. And the good news is, I would say, and the experts here, Norbert, Richard, you can correct me, I would say that most quantum information papers today, they do use some form of time frequency analysis under the hood. But it's hard to recognize if you don't know the language. And so why are there not more collaborations? And I would say there's two reasons. So two bad news, pieces of bad news. One is we use very different language, so it's just hard to talk. But it's not the only difference. The other one is that we work in a very different limit from your limit. And I would like call it the discrete versus the discretized picture. We are discrete and you are discretized. I want to make precise what I mean by that, or that conceptual, like as precise as it will get. So let's talk about an integer in a computer. It can represent two different things. Yeah, it could be that actually you want to measure some physical quantity that is a real number, or maybe it's discrete but unbounded. And then this integer in a computer is just an approximation to the reality. And that's what you use in engineering, in many parts of science, in signal analysis. But of course, if you have an integer in a computer, it can also be an exact element of some discrete group, or maybe some finite field. And this has also applications in combinatorics, in coding theory, but these two interpretations are very different in the end. So, I mean, when I see this, clearly, you live in the first world. Yeah? And in fact, I got a quote from your YouTube video, and you talked about a discrete approximation of a continuous reality. And in quantum information, I draw these pictures, and I think they are discrete representations of a discrete reality. So for us, really, these objects are finite. They are not, compressions of continuous unbounded reality to a finite set. That's not at all how we think. And this has this leads to differences in the kind of questions that we ask. Okay, so let's, for example, look at the typical regime that would be typical for a discretized time frequency analysis, and it's the regime you work in. So for example, you could work with a phase space, which is mod 500. So 500, you do many points, maybe you don't see that you wrap around, so it kind of, maybe it approximates something continuous. But, it's two-dimensional, the phase space, position, momentum, or time and frequency, that's it. And so, that is the kind of, regime I saw in your notebook here. And so, for example, the dimension of the phase space functions would now be 500. And that's, I think, the reason you gave. You said, I took 480 because, one reason is it works well on my computer. You said, I think now I could use 2000, because computers have advances. All right, here's, sorry, yeah. I will come to that in a second. Yes, I like this a lot, yes. So the typical regime for a discrete time frequency analysis in quantum computing is we put the 500 not in the base, but in the exponent. So we have Z2 to the 1000. You say, but Norbert's pulse is not going up at all. He was like 1000, so, that's Monday, but then, you know. Right? So it means, for example, that the dimension of our phase space functions is 10 to the 300. We also like to take the limit of n going to infinity. We also like to take the limit of n, the exponent going to infinity, actually. So clearly, we are working in a very, very different regime. Yeah. First, d is small, because d counts the internal degrees of freedom of some particle, and that's often 2 for a spin 1/2 particle, maybe 3, but then it kind of stops. But n is a number of particles, and that is ginormous. Yeah, it is thousands in a quantum computer if we could build it, and unbounded in reality. And right, so in one way, for example, if we make d very small, for example, d equal to 2, then the time frequency shifts, they collapse to the Pauli matrices. You can say nothing interesting can be said about Pauli matrices. It's 2 by 2 matrices. Well, but if you tensor them up 300 times, 500 times, then suddenly interesting structure appears again. And okay, fine. So I think this is one of the reasons why sometimes it's hard to match these two programs up. Yeah, because the type of problems that are relevant here and the type of problems that are relevant there are very, very different. Good. So now this was, like looking at the regime in which these methods are applied. What are they applied to? Okay, so finite phase space methods, not under these names, are used extensively in quantum error correction, quantum circuit design, simulation of quantum computers, toy models for quantum many-body theory. Each of this bullet point you can put into Scholar, and you get 2 million results, 1.9 million results, 3.7 million results. These are huge fields. And so, so I could now, at this point, I had to make a decision of what to present, because I could have done one of two things. I could have said, okay, I give the most pedagogically useful presentation of what is the most useful application of these time frequency techniques in quantum computing, and I would have probably selected quantum error correction. No, that's probably easiest and most important. Or I could come up with another application. There's some niche fields, like, for example, quantum combinatorics. And now, and now which one did I select? Oh, there's the winking Euler. Okay, so now I will tell you about, an application of these methods, not for these billion-dollar, big research schemes, that where they are used in hundreds of papers every month, but in a bit of a niche field for a number of reasons. A, I like it. B, it originates in Vienna. And C, I just had a paper the other day on it. Okay, good. So it also means the following. If you kind of now, have tasted blood, and you say, oh, wow, I know time frequency stuff. Quantum is doing it. Quantum gets billions of euros. I want part of the pie. Yeah, this is true. You should totally, try to get something from the pie. And if you're now disappointed with the second half of my talk, because I talk about Euler and useless combinatorics, this blame rests entirely on me. So in reality, the thing is actually, useful to a billion-dollar endeavor. Okay, good. This ends the first part of my talk. Is there anything we need to discuss? Any comments? Did I say anything wrong? He shrugs. Okay, very polite. Thank you. Okay, good. So then I will move on to the second part of my talk, which is maybe the actual part of my talk. And I will tell you about a problem in quantum combinatorics and how we use time frequency methods to solve it. And it aims to highlight my claim that this D value, the cyclicity of the group, we keep very small and take that very seriously. But before I talk about quantum combinatorics, I will motivate the problem using some extremely classical combinatorics, some very old school stuff, very old school indeed. Okay, I will talk to you about Latin squares. Huh? Okay, good. There's some who had this on their bingo cards kind of joke to be made here about Latin squares and bingo cards. I don't know. Okay, so what's the Latin square of order D? I think most of you will have seen that before, and it's almost recreational mathematics what I'm doing now. So Latin square of order D is a D by D table with entries in ZD, for example, or D different symbols, such that no entry repeats in any row or any column. So here are very small Latin squares, which embarrassingly I created using Mathematica on the train here. Okay, so The first row is 0, 1, 2, no repetition, 1, 2, 0, no repetition, 2, 1, 0, no repetition. Yeah, you can check. No, these are indeed two Latin squares. So these things exist. Let's make it a bit harder. So two Latin squares, K and L, are orthogonal if the following is true. Now I look at them both simultaneously, and I look at these pairs, Kij, Lij, where Ij ranges over the indices of the Latin square. And I want that these pairs take every possible value in ZD squared. Okay, so let's check that. So what I did is I took these two, K and L, and so to make it easier, I plotted them in one diagram. So every position here is now this pair. So 0, 0 means there's a 0 here, a 0 there. 1, 2, 1 here, 2 there. Okay, and you will see that every of the 9 possibilities occurs exactly once. 0, 0, 0, 1, 0, 2, 1, 0. I didn't cheat, no? So these are a pair of orthogonal Latin squares. So in particular, this structure exists for at least one value of D. They have, okay, now I'm bluffing. I shouldn't say that before, no? They have applications in combinatorics, coding, and statistical design theory, I just claim. I read this in some review article. I just think they're pretty, I couldn't, now please don't ask me what they're actually used for. But there's review articles in like operational research journals or something. They must be important for something. I can tell you what the quantum version is going to be used for in a minute. Okay, good. And now these go back a long time. And in fact, in 1781, so very classical, Leonhard Euler asked for which orders do orthogonal Latin squares exist? Because that's not so obvious. I just gave one constructive existence proof, but in general, it's not so clear. Because it's why was he interested in that? No, because it's so important for the applications in operations research. No, it's because it's beautiful math. Why else? I think. Okay, so and this was fully answered only in 1959. So this is a difficult problem. Yeah, it took a long time, and many eminent scholars apparently were. Okay, so let's try to understand when this is easy and when this is hard. Okay, so I now tell you how to construct orthogonal Latin squares, and today with like finite field arithmetic, there's many cases which are super easy. Yeah, and so here it goes. So let's say we have a finite field FD. See, we're doing combinatorics here. There's no discretization. We are taking our finiteness very seriously. So consider a finite field FD, and we take an element of FD, and it shouldn't be 0 or 1, which means also D can't be 2, because then I can't make this choice. But every finite field that is not F2 will have an element alpha that's different from 0 and 1. And now I choose my two tables in this way. So Kij is just I plus j, and Lij is I plus alpha j. I claim that these two tables each are Latin squares, and that they are together are orthogonal. And it's very easy to see. Let's first see that they are Latin squares. So let's look here. So I plus j. Let's fix j, so we fix the column, and then we range over I. Well, because addition is invertible, this will just be a permutation of all elements of the field, so no repetition there. And of course, it's invariant under the transpose, blah, 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 same here. Now I have to tell you that they are orthogonal. To this end, I write the same thing slightly differently, namely I give a matrix representation of the same equations. But now this matrix has determinant, here, it has determinant alpha minus 1, which by assumption alpha isn't 0, so this matrix will just reshuffle all d squared values, so we are done. But that was extremely easy. Don't get used to that. That's what I tell my students every time I solve a problem. Okay, so we have now found in like 3 minutes that orthogonal Latin squares exist for any prime power, because then we have a finite field, that isn't 2. So we have infinitely many just like that. Now construction part 2, that's, the next one is products. So it turns out if I have a pair of orthogonal Latin squares, one of order D1 and one of order D2, then I can multiply them together in a suitable way to get one of order D1 times D2. And how is this multiplication done? Maybe I don't go, it's super easy, but maybe a bit annoying to see. You say the product, now you take double indices. So the product where now the rows are indexed by I prime and the columns by JJ prime, they take now value in tuples, right? One from the first and one from the second. And if you think about this for 1 second, you will see that under this obvious product construction, there's a couple of primes missing, Yeah, that's right. There is a prime missing there and there. So at some point, like when I was young, I was using this hilariously named Beamer LaTeX package for my talks. And then at some point, I decided I'm now too old for that. And I transitioned to PowerPoint. And many things are much easier. I can put a smiling, blinking Euler into the slide with one click of a mouse. But getting the primes right is a super pain. So yeah, okay, I apologize for that. It's also, I think, a distinction between mathematicians and physicists. The mathematicians, they stick with LaTeX slides until they retire, and the physicists at some point give up. Apparently, yes, I think I transitioned in life then. Okay, good, okay, fine. So now, in any case, what is now, I can combine these two results, and that covers almost all the numbers. Namely, in every prime power, I can get one. And now if D is an arbitrary integer, I can just look at its prime decomposition. And for every prime power factor, I can use a finite field construction, and then I can multiply them together. And this works, and the only set of numbers where it doesn't work is if D is equal to 2 times an odd number. Because for 2, the finite field we had to exclude. Yeah, 4 times an odd number is fine, because the finite field of order 4, it worked, but 2 times an odd number doesn't work. Okay, good. And so now you are all as smart as Euler, because that's as far as he got. Okay, there's one more piece of information. It's very easy to see that there is no pair of OLS for D equal to 2. You prove it by realizing that there are only 2 Latin squares, and they aren't orthogonal. You just write them out. So nothing to be done. And so then, it leaves all the 2 times an odd number values open for the odd number being bigger than 1. So 6, 10, 14, we don't really know at this point. Good. So now we come back to this gentleman here. So he looked at this too, and he found these constructions. So I don't know whether he used the same tools or whether they were even invented at the time. I don't really know. But he tried very hard to find one in dimension of order 6 and couldn't. And for Euler, this was proof enough that it doesn't exist. He tried and he failed. And so he conjectured that, in fact, no OLS existed for any D, which is 2 times an odd number. So the one family where our construction fails, he existed, it can't be done. He conjectured it can't be done. And he gave the shortest, like the first special case. He gave as a brain teaser, and I put it here, but don't read it now. I see people starting reading, because it's just the same question we formulated, but except instead of numbers, he uses officers, because it was a very militaristic society. Okay, I'll read it out for you, but if you don't get it, because these terms don't stick in your brain, then this is fine. So he said, okay, let's see, are there 36 officers from 6 regiments? And each officer has one of 6 ranks. He said that's the first and the second coordinate here, right? And you want to arrange them in a 6 by 6 array so that each row and each column has one officer from every regiment and every rank. Just saying there is no repetition here. However, but I don't know any military ranks except for general, I guess. I couldn't name 2, and certainly I can't name 6. So it just became important. It became famous under the puzzle of Euler's 36 officers. Whether you can do it. So that is the special case, the first special case. And apparently, I read that a putative counterexample to this conjecture is known in the business, in this combinatorial business, as an Euler spoiler, which I think is a very nice term. Also, if you type it in PowerPoint, which of course you'll never know because you're all mathematicians using LaTeX, but if you try to, it will put a little red squiggly line under N because it thinks that Euler, even though it starts apparently with a vowel, is an EU, so it should be pronounced U, so it actually starts with a consonant, but of course it doesn't PowerPoint. It's Euler, not Euler or something. Okay, is an Euler spoiler. Okay, that's what happened in 1781. And then nothing. Thank you. Very good. Excellent. Nothing. I wanted to, highlight the nothingness with Fridas. Nothing happened for 120 years. There was nothing that happened. And then a bunch of stuff happened in quick succession. First, in 1900, a guy called Terry proved that T equal to 6 has indeed no solution. Euler was right. The 36 officers of Euler's do not exist. But conversely, in 1959, Parker, Bose, and Shikandi found Euler spoilers for all the remaining orders. So Euler didn't get it right. Just for 6 he got it right, where they don't exist. Well, no, 2 is excluded. Okay, 2 is trivially excluded. 6 is 120 years of hard work excluded. And all the other ones actually can be done. Yeah, most of which we already did, and the remainder Parker, Bose, and Schikander solved in 1959. So now the problem is solved. For every order, we now know whether there exists one or not. Problem solved. Or was it? Oh, well, no, that's not the right question. Norbert's asking what's special about 6. The question is, has the problem been solved, or will there be a sequel? Okay. All right, let's put this on hold. Let's talk about some quantum combinatorics. So after yet another 100 years, from the Terry, not from the research started on a field which could be called quantum combinatorics. I'm not sure there is a definition of what combinatorics really is. Yeah, it's you know it when you see it kind of situation, and also I'm not sure there's a definition of quantum combinatorics. It's somewhat to do with extremal configurations in Hilbert space or whatever. I'll show you what I mean by this. And so this is very relevant here because the first systematic study I'm aware of was a PhD thesis by a guy called Gerhard Zauner at the University of Vienna. And of course, I knew about his work since 20 years or so. But I've never really, looked up how things were connected. And yesterday on the train, I checked out who the advisor was, a guy called Neumeier. And so I checked out the web page, and he's sitting right there. And so I wrote him an email yesterday from the train at 7 p.m. and he's here. Thank you for coming. So exactly that's how it started. And then I also found that Gerhard Zauner, the PhD student himself, he never worked in academia. Apparently, he worked in mobile communications and did the PhD thesis on his spare time or something. But he has a web page with an address in Vienna, so I wrote him too. And he answered within 5 minutes and said, "Oh, yes, David Rose, I know you from your time in Potsdam," which is right. I was there 20 years ago. And he would have come, but he had a prior engagement today. So, okay. So, yeah, that's when it, the first systematic work started. And it's, been kind of big since. And so there's many different quantum generalizations of combinatorial structure, but there's one structure that frequently turns up in, for example, quantum codes, teleportation protocols, toy models of quantum gravity, integrable many-body systems. And this structure that I'm now going to define can be interpreted as a quantum generalization of orthogonal Latin squares. All right, what's not to love? Let's look at quantum Latin squares. Okay, and now it's going to be a little bit, that's, everything is so beautiful, but now we're going to talk about tensors and reshuffling of indices, and that's going to be a bit not so nice. I hope I can make it up to you later. Okay, so I give you now a definition, and this will sound completely bizarre to you. And I will later, like in 10 minutes or so, I will try to say a bit more structurally what's going on. So for now, please consider a tensor. Like 3 words you don't want to hear in a math class. Consider a tensor. Consider a tensor Tijkl. Oh my God. So it's an object with 4 indices, Ijkl. And each of them ranges, takes values, like d different values. For example, 0 to d minus 1. Okay. And now if I, God forbid, if I gave you one of these things on paper or maybe in a computer, then what you could do is you can group these indices together to form what's called a bipartition or a matrixification or a reshaping, many different ways of talking about it, to get a matrix which represents a linear map from cd squared to cd squared. So for example, I have examples here. Okay, let's look at this below first. For example, I can define a matrix Uij. Ij is now seen as one index, and Kl is seen as another index, and that should be Tijkl. Yeah, and so this now takes d squared different values, that takes d squared different values, and now you get a matrix from cd squared to cd squared. Okay? But there are different ways of bipartitioning those indices. Yeah, there are in fact 6, but up to reordering, there are 3. There are 3 different ways of grouping these 4 indices into 2 pairs. Okay, and they have names, and I'll draw something on the board in a second so that you can remember it better. And a tensor T is called perfect. What a nice name. It's called a perfect tensor if all such matrices are unitary. That's completely bizarre. Bear with me for a second. Okay. So yeah, and so these things, these perfect tensors, we're going to look at now. Aha. Now there will be a comment by the gentleman from Paris, and I put it on my slides after he skewered Richard on that, because I've chosen a basis to say that. Not only have I chosen a basis, I've defined a mathematical structure in terms of reshuffling of indices. That's probably the least respectful way you can introduce a mathematical structure. No, I mean, there's people who like MATLAB and Python and Julia on the reshapings, and they go like, yeah, whatever. But if you're like a mathematician, you would not consider this a serious. I mean, come on now, what is that? Okay, and one part of our project that I will report in 10 minutes is to give an invariant interpretation of what's going on, but not quite now yet. And Norbert, you can try to think whether you can find it until then. Okay, good. Okay, let me just. Yeah, it's maximally entangled across every card, which is equivalent to the matrixification is unitary. It's not stated there in this. Yeah. Sure. I give an even more abstract. It's okay already. It is in fact base independent, but I can state it as a property of star algebras. Just bear with me for a second. Okay, good. So now, okay. So what would you do in practice? In practice, you would not start with a tensor, but you would start with one of these unitaries. So now you have to find these. How would you find this? I mean, absurd. Yeah, you can't. Yeah, it's an absurd problem. Yeah, you rearrange numbers and then you compute the sesquilinear outer product. Yeah, it's a sesquilinear one, so you can't. Otherwise, the people from Linz would tell me I should use Buchberger's algorithm to find a Gröbner basis, but it's sesquilinear, so you can't do it. So it's completely unclear how you should even start. But how you would start is you would start with one of those matrixifications. And so we like also, Richard already, maybe this way, Richard already indicated we have this graphical notation for tensors where every tensor is a box and every index is a line. And then like reshuffling of indices I can talk about very easily in this picture. So for example, now I look at the second matrix, U gamma, and the gamma is quantum information notation. It's half a transpose. You take a T and cut the T into two halves, and then half the T is a gamma. So that's a partial transpose, where a transpose normally is if you exchange all indices on the left and on the right. But here what you do is you exchange only the upper ones, but keep the lower ones intact. That's now the partial transpose. So that is unitary, that's easy to do, but this also has to be unitary. And now the other one is called the reshuffle, where you exchange the upper index on the one side with the, how can I do it? With the lower index on the other side, like this or something. Not sure I've advertised this as a good way of thinking about it. In any case, so you get a matrix and use. That's the composition of a swap and a partial transpose. That's right. Yeah. So okay. So somehow quantum people like to fiddle around with matrix indices, and they demand that their objects remain unitary under this. Okay, good. I have some uphill battle now to convince you that this makes any sense. Okay, good. So here's now. Okay, this was like a bit of a downer, like matrix index reshuffling. Now let me tell you about a cool application. Why people care about this so much. And there is zero chance that you will understand what I'm saying now. That's all going to be words, but I hope these are pleasant sounding words so that they convince you that this actually is not just a waste of time. If you have any questions about this research problem in particular, then I'm also not an expert on it, but you can see there is this guy Preskel, which also was on the slide of Richard, and this was published right around when Richard was working there, so it was probably done in your office at Caltech. Next office? Yeah, next office. Okay. Also, if you have real in-depth questions, Norbert is the local expert on this. Okay. So here's the thing. So people try to find this, new theory, for example, of quantum gravity, and we have no idea how it works. And so what they then do is they have some heuristic properties that they believe a quantum theory of gravity should fulfill, and they try to find a theory to match up with this. And so one of these heuristical things that we believe might be true, but nobody can make it very precise, is called holography. And it states something like this. So everything that's measurable in the interior of a region can also be measured on the boundary. Okay, whatever that means. And it's a bit unclear whether you can find a quantum theory with that property. But then, if you have these perfect tensors, you can. So that's one of the reasons people are interested in this. Let me just walk you very quickly through it. You can't understand it, just that you get an idea of what we are up to. Yeah? So in this diagram here, every red dot is a tensor. That's the mathematical part. Every edge here is a leg. And every tensor has 5 legs going out and 1 additional leg sticking out of the diagram, so it has 6 legs. My tensors only had 4 legs, but that's just because the picture I found in the paper had 6. You can do it with any even number, so you can also use mine here. And so how do you interpret this? You interpret it like this. Every red dot sits on a position in space. What you do is you discretize space. You have a lattice model of space, and so for every, I guess, Planck length unit cell, you got 1 degree of freedom telling you what are the properties of physics measurable at this point. Okay? And so the index sticking out here is a Hilbert space that corresponds to this region in space. But they are all connected. They are all entangled, if you want. So if you, right, okay, so now if you, this thing, if you contract it out, where there's 1 index for every Planck scale cube, so talking about n is at the very least astronomical or galactic, but probably infinite. Yeah, so this is nothing you put into MATLAB. Yeah? So now this is a ginormous tensor, yeah, where the interior of the space region, these are all these red dots here, and here you see the boundary. And now I want to have the property that every operator that lives on finitely many of these interior points, I can rewrite the action of it. I can rewrite the action of another operator purely on the boundary. Okay? And so what you do is you go in a piecewise fashion. So you take a perfect tensor at every one of these things, and then the perfect tensor tells you how to integrate the information coming from the space-time point and the information coming from other pieces of space-time and push it through this network. And using the perfectness property, it means that somehow, however you traverse this spatial region, the operation is unitary, which in quantum language means the information is faithfully preserved. Yeah, and so these models that you can build here out of these perfect tensors, they show that this requirement that people in quantum gravity would like to have is not self-contradictory. It's called a toy theory because it says in principle this can be done. It's not suggested that this is actually how quantum gravity should work, but these were very influential. Look, yesterday it's cited over 1,000 times since 10 years. Yeah. To the what? I think yes. ADS, yeah, it's an ADS. Yeah, that's right. That's right. It's a hyperbolic space, and this is an ADS CFT is somehow like the heading. Okay, fine. I want to tell you that I like these combinatorial puzzles, but they're not just combinatorial puzzles. You can build models of weird quantum theories based on concatenating infinitely many of those. Okay, so now you're all motivated to construct them, no? No, so every tensor here, nothing is combinatorial about the diagram, but every tensor here needs to be a perfect tensor for the unitarity property. Well, very good. So Norbert says it's not a combinatorial problem. Let me show in my next slide that it is one. So, okay, thank you. No, on the next slide. Okay, oh no, maybe, okay. So now we have an existence problem, namely for which orders D do perfect tensors exist, because we need these perfect tensors to build these space-time models, for example. And here's a proposition which shows that they are combinatorial, as Norbert will concede in 1 minute. Namely, here's a thing that's easy to see, but I won't prove it here. Namely, if I take 2 arrays, K and L, then they form an orthogonal Latin square if and only if this tensor is perfect. How to read this? So E, I, E, J, these are unit vectors in D dimensions, and you should have implied tensor products between them. But in PowerPoint, the only tensor symbols you can do are ginormous, and it looked very ugly, so I deleted them again. So this is an order 4 or degree 4 tensor, and so okay, fine, so there is so you can characterize orthogonal Latin squaredness, this condition, as a perfect tensor condition. Clearly combinatorial, would you not admit, Norbert? And so it means we can leverage all the work done since Euler to build perfect tensors and to build space-time models and all that stuff. So now we know that there are perfect tensors for any D except possibly 2 and 6. Now it's easier to see that there is no perfect tensor for D equal to 2. And now you can all see where this is going, because there's one dimension where classically there cannot be such an object, but the possibility of a quantum generalization remains open. Now the question is, does there exist a perfect tensor of order 6? Sorry. Yes. Yeah. This is. It's neither no. This works for any even number. It just in this picture they had 6, but you can also you can do such a tiling. They are allowed to be complex numbers, but they're not required. Yeah, and so if you have a pair of orthogonal Latin squares, you can even get a perfect thing even with non-negative numbers. But this is the important point. The definition doesn't require it. So there could be a quantum generalization of the structure that involves complex numbers that is more general, but this could be true. You can also generalize it. Come on, like today I'm talking about the particular problem with 4, but you can, of course, you can look at generalizations for this. So it's a general. Yes. But it's maybe I would be happy if we could accept this for now. So let me say in which sense it's combinatorial. It's a quantum generalization of a combinatorial structure in the following sense, that every instance of this combinatorial structure I can turn into a quantum instance, but there could be more. So in this sense, okay, and then maybe. Well, it's like combinatorial is also not defined. Come on, it's okay. Look, for the purpose of my remaining 10-ish minutes, that is what I call a combinatorial. Okay, so but now you can all see where this is going, I hope, namely that we can leverage the classical solutions for all orders except for 2 and 6 because there are no classical solutions. For 2, there's also no quantum solution, but for 6, there could be a quantum solution even though there is no classical one. All right, so does there exist a perfect tensor of order 6? And that is again an artificial intelligence asked to draw a quantum Euler. Okay, and this was an open problem for some time. Here's a paper, 5 open problems in the theory of quantum information. Look at the names. No. The elements are complex numbers. Yeah, but the maybe we discuss this later because I'm running out of time. If it's a one-on-one thing, we should discuss later. If you think it's important for everybody, we can discuss it now. You think, and I go on. Okay, so
what does order?
Yeah, order is the dimension of the local Hilbert space. So 5 open problems in the theory of quantum information, and the third one was determine whether there exist 2 quantum orthogonal Latin squares of order 6. 2 quantum orthogonal Latin squares, that's another way to say perfect tensors. Many different people have different names for that. Okay, so it would be the ultimate Euler spoiler, no? Like a quantum solution where there couldn't be a classical one. If you like very bad mathematical puns, I would say it's the one bridge Euler didn't think to cross. Okay, I see myself. All right, good. So then this was, say there's no problem. Shortly later, there was a solution. So computer says yes. So in the year 2022, Euler plus 243 years, a quarter millennium later, there was a numerical search that did find order 6 perfect tensors. So the answer apparently numerically is yes. And there was a big splash, 36 entangled officers of Euler, a quantum solution to a classically impossible problem on the paper. And it was a very well publicized breakthrough. So it was in physical review letters, which is high impact or whatever we like it, the rector likes it. And there's like Quanta and Wired, they wrote articles about it, and YouTube went gaga about it, so it was very well publicized. So these are all very serious people, and I think the guy who did most of the technical work is Suhail Rava, here, the first author, and there's also Carol, who is a very nice guy and a very flamboyant person. I think if you know him, and if you don't believe me, put his name, if you can spell it, into Google Scholar, and you will agree with me that he's very flamboyant. And he really marketed as well. 36 entangled officers of Euler. Well played, Carol. Great scientific marketing. There's just one problem with these solutions. So here's from their paper. So what they did is they used a computer search, which is very difficult. I don't even understand the algorithm precisely because they're looking for a very thin set. It's super over-determined, the problem. So you can't just, I don't know, they use very smart numerics. But even though it was numeric, they later could find like every single entry of this tensor was an algebraic integer that they found numerically. So it was exact, even though it was a computer search. And so they have this table. So they divide out these indices into blocks. And then you have roots of unities appearing, even though nobody put that in. They have color codings, and the ratio between these coefficients are golden ratios for some reason. They didn't put that in, it just came out. So clearly, this displayed signature of an algebraic structure. But this remained unexplained, so they just had a computer solution. So that's now where my talk starts. Okay, so now what we try to do is we try to tie up officers with our bare hands without the aid of a computer. So we wanted to use nothing but maybe quantum harmonic analysis to write out these objects manually with pen and paper and no computer search. And that worked. So this is our contribution. All right, good. So first, I need to do the following. So perfect tensor was defined by ugly index shuffling. And then, of course, in this, mathematical context, people object to that. That's not nice. So the question is what's going on more structurally. And I will tell you I will give you now an invariant construction. And why do I do it? First, because it's more structural. It also has at least some connection to analysis. This is an analysis workshop, and I haven't talked about analysis at all. It uses star algebras, which I guess are studied by analysts. And also the story connects to this workshop. I will not tell you just now how, I will tell you in a minute. Okay, so now the next 3 slides are a bit technical. What is actually going on? If you don't understand it, it doesn't matter, because the rest of my talk will not build on it. So first, let MD be the algebra of D by D matrices. Okay, I will do it twice, first mathematical, then physically. Okay, so then if I have MD, I can also look at MD tensor MD, and this algebra contains 2 subalgebras, namely MD tensor 1, the left algebra I call it, and 1 tensor MD, I call it the right algebra. Okay. Now U is a unitary acting on this entire big space, and if I have such a big unitary, I can rotate, let's say, the left-hand algebra. I can conjugate it by U, I get a new subalgebra. Let's call it A for algebra. Fine. Okay, now I want to measure how far away A is from L. Now, algebras are subspaces, and on these matrix algebras, I have the trace inner product, or the Hilbert-Schmidt inner product, if you want, and so I can use this to quantify how far they are. So ideally, for reasons that you will see in a second, I would like them to be orthogonal as subspaces. Now that's impossible because they both have the identity. They're both unital. So I want to say, okay, I want them to be orthogonal except maybe the identity. And this notion is called quasi-orthogonality in the study of star matrix algebras. So we say 2 algebras are quasi-orthogonal if their trace-free elements are orthogonal to each other with respect to the trace, also known as the Hilbert-Schmidt inner product. Okay, now I can say what I mean with 2 algebras not having anything to do with each other. Okay. Now I will tell the same story physically. I will tell you exactly the same thing, but give a physical meaning to it. So MD tensor MD is the observables of 2D level systems. Stuff we can measure. And so the local observable stuff I can measure on the left is this, and that is stuff I can measure on the right. The unitary is a reversible process acting on these 2 systems. And so A, which is the rotated version of L, is quasi-orthogonal to L and R if and only if, after applying U, no property of L is accessible by performing local measurements. Okay. Let me give you an example of what this means. It's a classical example, easier to understand, and it's called the one-time pad. One-time pad works like this. You get 2 bits. L is the message, and R is the key. And what I will do is I will take the XOR of the 2 bits. Now I have L XOR R, comma R. If I give you, that's a reversible operation. But if I give you the ciphertext and the key, then no local measurement will recover the message. If you just look here locally, you have no information about the message. If you look there locally, you also have no information about the message. So this quasi-orthogonality property, this is some kind of quantum generalization of a one-time pad kind of structure. Now we have our algebraic characterization of what a perfect tensor is, which hopefully will prevent any complaints that I'm just doing basis-dependent stuff. Okay. Now we prove that U is, if U is a unitary, then this funky partial transpose is unitary if and only if U star is quasi-orthogonal to R, and this UR is unitary if and only if the same is true with L. And so maybe in other words, if I summarize this all, perfect tensors exist whenever you can hide a local system worth of quantum information in a bipartite quantum system. So if you can take local observables and delocalize them. So it's just about the existence of certain matrix star algebra decompositions. So if you like that, then you can help me solve the problem in this language. I'm running out of time. I have to speed up a little bit. One story I need to tell you, because the main ingredient to the algebraic characterization is a result of this paper, which links to the workshop, because apparently the workshop started with a paper by Reinhardt, and it is a paper I wrote together with Reinhardt. In fact, the only paper I ever wrote together with Reinhardt. And you can ask, where was it written? And it took 2 years to write, so it was written in many places. But if you look at the acknowledgements, one of the places where it was written was right here. We wrote this right here, and this is part of the result. Okay, good. Good, fine. Now I have 3 minutes to talk about phase space. I will just make it very brief now. So how did we now, in the end, actually solve this problem? And there is a phase space formulation. And this, you can use this algebraic characterization, a bit of algebra. I can't do it now. But here is a harmonic analysis characterization. So let lambda be a function on a phase space. So lambda is a complex valued function on a finite vector space with a symplectic form on it. That will be important. Okay, so then there is a way of, if lambda has certain properties, of getting a unitary that comes from a perfect tensor. Don't look at this construction because I don't have time to explain it. It's a kind of circulant structure and a twist structure, and we were exchanging emails about the structure before. Okay, but don't look at it. I will tell you now what are the sufficient and necessary conditions on lambda to get perfectness. Lambda is a function on phase space. First, lambda has to be unimodular. Absolute value has to be 1. Already, if you take discretized mindset and let n go to infinity, probably doesn't make much sense. But for finite ones, it makes sense. Then the domain is a vector space, so it has addition. So I can define a convolution, and I can define cross correlations. That's the usual definition of the cross correlation, but everything is discrete. So first, the function should have no autocorrelation. If I cross-correlate it with itself, it should be 0 whenever it can be. But that's not the only one, because, and also on a phase space, you don't just have convolution, you also have twisted convolution. Aha! So you can also define twisted autocorrelation, which is autocorrelation with this twist, which comes from the Weil-Heisenberg composition law, and which also featured in your talk on Monday. And so also this lambda must have no twisted autocorrelations. And if you can find a function with all these 3 properties, then you're done. Then you've constructed the perfect tensors, and you can go out and construct space-time models. You need unimodular, no autocorrelations, and no twisted autocorrelations. And at the time when we started, no analytical solution was known. Okay, so then the question shifts here. Now I have no time anymore. So I could have shown you how to construct one. It's very easy, but I don't have time, so I don't do it. It also boils down again to a determinant condition, so it's kind of related to actually the construction I started with. In particular, the resulting unitary I get, the U, the UR, the U gamma, they're all metaplectic. So they all have little symplectic matrices. So in the space-time model, there are little symplectic matrices in every Planck scale unit cell. All right. And okay, and then we had to, now comes the actual result, but in this moment, I'm out of time. Okay, so there is some obstruction against a simple construction using Chinese remaindering, which we call the Great Wall, because it's an obstruction that's Chinese. I hope that's acceptable. Blah, blah, blah. Now we come to your divisor thing, but we can discuss later. So these divisors become very important. Okay, and so now the final thing is that we can play some tricks of taking Z6, and 6 has these co-prime factors, 3 and 2, which kind of don't work well with arithmetic, but we can shoehorn it into a union of 2 different vector spaces over a finite field, actually. And if we do this as a nonlinear operation, And if we do it, we get an explicit handmade solution to this problem that combines two symplectic operations. It partitions up this phase space over mod 6 into two smaller phase spaces, mod 3, and combines two different symplectic operations. And we can do it, and we can complete. They're essentially unique. We can characterize them up to symmetries and everything, so we know exactly how many solutions there are. And it's as close to metaplectic as you can get. Okay, fine. So sorry, now I didn't run out of time in the end, but here's my summary. So quantum computing is a $1 billion endeavor that runs on discrete time frequency analysis. But you wouldn't know it because they work in the small d large n limit, which is the orthogonal limit to what you showed us on Monday. And if you do take the small d seriously, it becomes natural to look at combinatorial kind of questions, which we took very seriously in the run-up of this workshop. And for example, you can look at quantum orthogonal Latin squares, because why not? Oh, does it generalize for 2 times odd? Of course, I thought about this, and I don't know. I have no idea. So now we can again use this multiplication trick, which also works in the quantum case, and we have solutions of this form for almost all dimensions, but for 2 times odd, where the odd number is not a multiple of 3, we still can't do it. And I don't know whether it works or not. I tried, but I don't know. It's a good question, and I don't know. If Gerhard wants to do another thesis. So. Yeah. Yeah, that's a holographic principle, yes. How general? No, I don't think, no, I think we don't know. So when a physicist says the word principle, it's an interesting word. No, we have like axioms or laws of natures or something, and sometimes we have principles. And a principle is I guess a heuristic or something. It's something that is a bit more well-informed than a wild guess, but we really don't know. So the holographic principle is a principle, meaning we kind of believe that it's probably something general you find, but we don't really know. But it's certainly not intrinsically tied to hyperbolic space. No, it's just there you can actually come up with toy models. No, it's not. It's pre-mathematics. Yes. It's kind of even pre. I don't know. Yeah. It's very speculative, all of this field. I'd be right.